Hello everyone, hope you are all doing good. So today let us continue our discussion on the conformation of the substituted cyclohexane. So if we remember what we did in the last class, we saw how to draw methyl cyclohexane in the two different chair conformations, okay? And when I tried to tell you about the abundance of these two conformations, I told you that the substituted form in which the methyl is present in the equatorial position would be more abundant than the conformation in which the methyl group is present in the axial position. So I asked you to look for why there is a inequilibrium present in this case. Like, what is the reason why the conformation in which methyl group is in the equatorial position is more abundant than the one in which methyl group is in the axial position? So that is what was the question that was posed to you. And I asked you to look into two important factors, two ways in which you can look for. One was to draw the Newman projection formula, okay? And the second thing that I asked you to look for any kind of steric effect in the structure, okay? So I hope many of you did try and would have come on similar grounds, similar explanation that I'm going to give today. Okay, so let us see why there is a difference in this equilibrium when it comes to substituted cyclohexane. So let us try to draw the Newman projection formula first for the conformation in which methyl group is in the axial position. So if we look at this today, we are going to draw the Newman projection across the 1,2 bond as well as across the 5,4 bond. So if we are looking from this particular side, we see that the second carbon and the fourth carbon are the front carbons, okay? And the first carbon and the fifth carbon, they are the backside carbons. So when we draw the Newman projection formula, the front carbon, that is 2, would be coming as a dot, and the back carbon, that is your carbon number 1, would be coming as a circle. Okay. And similarly, the front carbon here would be the fourth one, and therefore that would be represented by a dot, and the back carbon is your fifth carbon, and that would be represented by a circle. Okay, so this two things we have drawn for this particular bonds in this case. Okay, so let us now try to connect, because this 2 and 4 are joined to carbon number 3 in an upward manner. Okay, it is joined in an upward manner. So this is your carbon number 2 and this is carbon number 4. So they are joined to 3 in an upward fashion. So that is why I drew the structure something like this. Okay. Similarly, when you look at back carbon, that is carbon number 1 and carbon number 5, they are joined to carbon number 6 in a downward fashion. So that is why I drew the first carbon and the fifth carbon joined together into the sixth carbon in a downward fashion. Okay, so these structures are complete. Now we have to draw the remaining bonds. So first let us look into the second carbon. This we have understood, this is one bond. So obviously the other two bonds would be oriented at an angle of 60 degrees. So that we drew something like this. Similarly, we will draw on the fourth carbon atom. Fourth carbon atom, this bond we already drew to the carbon number 3. Then obviously the other two bonds would be oriented at an angle of 60 degrees. Similarly, we will draw for the back carbons as well, because we now have drawn for the back carbons the attachment to the sixth carbon. So obviously the other bonds that are attached would be at an angle of 60 degrees to them. So once you draw them, Now we have to add the substituent. So if you see this carbon number 2, this is bonded to 2 hydrogens. Obviously, the 2 bonds that you have drawn here, they would be attached to hydrogens. If you come to the back carbon, that is carbon number 1, uh, it is attached to 1 methyl and 1 hydrogen. So methyl, since it's oriented in the top direction, this would be the bond in which you have the methyl group, and the other bond would be the one containing the hydrogen. The rest of the carbon atoms, they all have the hydrogens. Okay. So this is how you drew this particular structure. Now, the question posted, you might be having in your mind that when we initially drew the Newman projection formula for a chair conformation, we took these 2 bonds, right? The 2,3 bond as well as 6,5 bond. So why we are this time making the Newman projection in a different way, like choosing these 2 parallel bonds? The reason why I am choosing these 2 bonds is because this is the carbon atom which is containing your methyl group. Okay, so it is very essential for us to take that bond. Only then we can know the conformation of this particular methyl group with respect to other atoms or groups. So that is why I choose this particular bond, because only in this bond you will see the methyl group conformation. If you check this bond, it will not have the methyl groups, all are hydrogens, which is not our uh, concern right now. We have to check because the instability is coming because of methyl group. So we have to check why this conformation is affected because of the orientation of the methyl group. So that is why I took the bond in which contain the methyl group. Okay, so that is why I choose these 2 parallel bonds and took and drew the corresponding Newman projection formula. Similarly, in this structure, when you draw the Newman projections, and this is the one that is carrying the methyl group, I'll choose these 2 parallel bonds, that is 1,6 as well as 4,3. Okay, so that is what I drew in here. Probably, I think here I have chosen these 2 bonds in this, because this one also you can choose, that is 1,6 bond and 3,4 bond, that you can do as an exercise. Probably in the live session, we will try to draw using these 2 bonds, because here also these 2 bonds also contain methyl groups. So you can draw the Newman projection considering these 2 parallel bonds. Okay, but in this structure that I have drawn in here, I have chosen these 2 bonds, that is 1,2 bond as well as the 4,5 bonds, because that is the bonds that I have chosen in here, that is 1,2 bond as well as the 5,4 bond. So for a similar comparison, I choose the same orientation, same carbon atom, that is 2,1 as well as 4,1. So likewise, in the first structure where 2 was a front carbon, so you are looking at the structure from here. So second would be the first carbon, first would be the back carbon. Similarly, fourth would be the front carbon, fifth would be the back carbon. So accordingly, you drew the corresponding Newman projection formula. So I'm not explaining this particular structure. So I hope you understood how to draw the Newman projection formula. If you have any doubt, you can continue to ask about the same. So I'm not using any discussion right now. I hope you're going to do yourself this particular discussion. Now, if you compare these 2 Newman projection formula, one in which your methyl group is in the axial position and another in which your methyl group is in the equatorial position. So what is the difference between these 2 structures? So if you look carefully at just the methyl group here, okay, now this methyl group is in close proximity to this particular carbon number 3, that is basically here it is CH2. Okay, so this is this bulky methyl group is in close proximity to another bulky CH2 group. Okay, so because of that, what will happen? There is a kind of interaction, kind of steric interaction that is possible because of the close proximity of the methyl group with the group, a bulky CH2 group. Okay, so this type of interaction is occurring in this structure in which they are in close proximity. However, this particular Newman projection formula, where you have drawn it for the corresponding conformation in which methyl group is in the equatorial position, you'll find that this particular methyl group is nowhere close to any other bulky carbon group, but rather they are it has its as its neighbor the hydrogen atoms. So it's not sterically hindered at all. Okay, so this particular structure in which methyl group is in the axial position, you will find steric interaction, and this particular interaction in which the adjacent bonds are at an angle of at a dihedral angle of 60 degree, you will experience a steric interaction which is called as the Gauche interaction. Okay, so this occurs when the bulky group on the adjacent carbons are separated by a dihedral angle of 60 degrees. So adjacent, so we have two adjacent carbon atoms, that is 2 and 1. On these, you have the methyl group and the other carbon, that is the H2 group. They are in close proximity and they are separated by a dihedral angle of 60 degrees. And that is why you see this Gauche interaction, which destabilizes this particular conformation in which methyl group is in the axial position. However, when the methyl group is in the equatorial position, there is no Gauche interaction. So that is why the equatorial conformation, conformation, cyclohexane conformation with methyl group in the equatorial conformation is the one that is preferred over the ones in which methyl group is in the axial position. Okay, so this is one reason that you can come from the drawing of the Newman projection formula of these particular conformations. Now, there is one more reason just on the basis of steric interactions. So if you just read the structure of the one in which methyl group is in the axial position, you will find that there are two hydrogens also present at, like if you write this as first carbon, so 1, 2, 3. Okay, similarly 1, 2, 3. So, okay, so in both the way, there are two axial hydrogens which are kind of close proximity to the bulky methyl group. Okay, there is a kind of steric interaction that is possible with the bulky methyl group and the axial hydrogens. Okay, this also destabilizes the conformation in which methyl group is present in the axial conformation. So this particular interaction is called as 1,3 diaxial interaction. So it is a kind of steric interaction between the axial methyl group and the axial hydrogens oriented in the same direction. So this is the axial methyl group and the hydrogens are oriented in the same direction as the axial methyl group. So when there is a steric interaction possible in such situation, that lead to another destabilizing reason, and that is called as 1,3 diaxial interaction. So there are two destabilizing factors that actually destabilizes the conformation in which methyl group is present in the axial conformation. One is the Gauche interaction, that is because of the 60-degree dihedral angle. Another cause of instability of the methyl conformation in the axial position is the 1,3 diaxial interaction. Okay, so I hope this particular thing is pretty clear now to every one of you, why there is a stability difference that you see in the case of this particular conformation in which methyl group is in the axial position and this particular conformation in which the methyl group is in the equatorial position. So this was the last topic that we had in this particular module. So if you have any clarification, you can definitely come up with your doubts. So till then, have a nice day. Thank you.